Yeah, so just like I was saying, like we'll try to begin grading the exam today. Definitely should have them by tomorrow. And so once I have them done, I will send you like, like the usual grade distribution, like an idea of like what the scores were like and like, like the letter ranges, like the letter grade ranges for the exam. I mean, yeah, if the exam scores were lower, like, I will adjust the grades. I mean the ranges appropriately. I'm not too worried, at least in the sense that you had done very well on the first exam. So on I think I'll once I start grading them, I'll get like a better idea. But yeah, like I'll let you know once I have done all of that. Hopefully by some point tomorrow afternoon. Um, so today, just to tell you a couple of things. I don't know if you saw my announcement that I sent a couple of hours ago. Let me see, this still looks a little bit weird. Okay, no, this is here it is. The yeah has I don't necessarily want to spend too much time doing this but I do think it's kind of useful if it's a useful perspective. So I don't know, has everyone taken linear, just out of curiosity, has everyone taken linear algebra here, or someone's taken it, or someone hasn't taken it? Or more like in reality, you don't need to know that much about linear algebra. I was just curious whether you had ever multiplied two matrices together. So maybe I should put that in that I should ask it that way. So is that something everyone is familiarized with, or you can send it as a private message if you don't want to like respond in public to that question. But just to get like a better sense, like to not mention too much depending on what you say. But I think it can be useful perspective to have for some of the formulas that I'm about to tell you in a couple of minutes. Um, so yeah, but like, you can answer on the private chat if you prefer. Um, in the positive or the negative, just to let me know whether you have done matrix multiplication before. Um, so just to remind you, what we were doing last time is just so last time we were talking about, well, maybe you have like a function of one variable. Oh, sorry. Well, a random variable that is a function of another random variable, right? So, for example, the case with one of the cases we had considered last time was like y equals ax plus b, right? Which is just like a translate. But another case, did I do this other case? Oh, like y equals e to the x. Um, is another possibility, right? Like you start with a random variable and define a function of it. Okay. And what we were doing last time was kind of just to relate their density functions, which is what's used to compute the probability. There is like a more general formula that you can find. I will just do it quickly because it's just like good application of the fundamental theorem of calculus, and it will justify a law that sometimes is called the law of the unconscious statistician. So um, just to give you like some idea of what I'm trying to do now, imagine that maybe you have like I mean, it doesn't need to look that boring, but you have like a function y equals g of x. And so g of x is going to be some function which is increasing. And it has derivative continuous with derivative with differentiable. So like some examples of those types of functions would be like g of x equals like x cubed, right? Like that x cubed is an increasing function. Increasing, like you can just think about it as the derivative being positive, Okay, so for more concretely, you could just think of this as having positive derivative. What is another increasing function? Another increasing function um, would be like e to the x. That's also an increasing function. Natural log is also an increasing function. I mean, like other functions are increased. Like like you did this a lot in Calc 1, right? Like in general, what happens is like functions could be increasing or decreasing like for certain amounts of the interval. So there are more examples that you would find if you restricted yourself to like, particular intervals of the real line. I'm not going to get into too many details of those subtleties. It's more like just to have like some sort of like idea of how these formulas would look like. Already like the fact that the natural log and the exponential fall into this class of functions is good enough because the exponential and natural log are very important. I mean, they appear quite common in probability theory, right? So as you have seen. So once you have like a function like this, you could just define like a new random variable, which is just that function applied to the to an older random variable. So just think of this as an old random variable. And y, which would be g of x, is like the new random variable. So what does that mean? Like I just mean like that, when this random variable, for example, if the function that you chose is x cubed, that just like what this notation means is that when this random variable takes a value x equals 2, the new random variable takes a value 2 cubed, which would be 8, right? So it's just like saying that their values are related using this function g. So once you have the relation between the values, you could try to find like what's the density function for y. So here's like the question: what is okay? And so the density function, remember, um, to com to compute the density function, what we were doing last time was to first you would try to find like a useful formula for the probability that the random variable is less or equal to y, right? Because the density function is this probability can always be computed as the integral of this um, density function. So let's just think about what the probability of y being less or equal to y is. Um, well, there's y is g of x, so that's a probability that g of x is less or equal to y. Okay, but this is where you would use the fact that this is increasing. Like you can kind of see it here. Like if the first derivative, for example, is always positive, the function is always increasing. Then this function is what is called injective or one-to-one. And then if you restrict the domain appropriately, it will have an inverse. Like in the case of like x cubed, the inverse, right, is cubic root. In this case, the inverse is ln, and in this case, the inverse is e to the x, right? Again, for other functions like sine and cosine, like the inverse were like arc sine or cosine, those exist. Want to restrict the sines and cosines to a proper interval so that they become bijective. So I'm just saying like one way to think about this inequality, if since G would have like an inverse under the conditions we're working with, is that like you can apply kind of like the inverse to each side of the inequality. Is that making sense? Uh, so And then, by the way, the fact that this inequality gets preserved when you apply G inverse, that's where you're using the fact that this function was increasing. Otherwise, like the inequality would be reversed. It's not that much difficult, but is something to keep in mind. So you can also find something useful in the case like the function is decreasing, but like I'm just going to worry about the increasing case. So, and then what's the point of the inverse? If you remember, the inverse of the function, like the property is that it kind of cancels out the function g, right? So g inverse g cancels out. Similar, again, that's I guess one reason why I asked if you had taken linear algebra. That's something you see more common if you take linear algebra with matrices, right? Like you have a matrix, you have it, like the inverse of the matrix, and A inverse times A gives you the identity matrix. So the version for functions, like more ordinary functions is like G inverse G is like the identity, or it just means like it just gives you back the input that you started with. So this is just a probability that X is less or equal to G inverse of Y. Oops. Is that making sense, everyone? Are there any questions up to this point? Are we good? Um, And so this, again, once you have like the probability in terms of X, the original variable, the original random variable X, that by definition or kind of by the properties of this function, this density function, probability density function, it's literally just the integral from minus infinity to this value of the density. Okay, so what is the density for Y? Well, if I think I gave you that formula a couple of lessons ago. Maybe it was like maybe it was last time. Right. The density is just like the derivative of with respect to the variable of this integral. So yeah, this is sometimes called the distribution function. I think I said it last time, but I don't remember now if I said it. But so the density can be just found by the taking the derivative with just like the fundamental theorem of calculus. So this is just a derivative with respect to y of the integral from minus infinity to g inverse of y of f sub x dx. And again, to write that in a more convenient way, you can just use the chain rule. So this like because the problem with this as it stands is that you don't have y as the upper bound. If you had y on the upper bound, you can just use the fundamental theorem. So what I'm going to do now is just you like a u sub where u equals g inverse of y. And so this is just the integral, sorry, like by the chain rule, this would be the derivative with respect to u of minus infinity to u of f sub x dx times du dy. Okay. And so that gives you what, again, when you see this now you can apply the fundamental theorem and this derivative cancels this integral and you just get f sub x of u times du dy, so times the derivative of, oops, times the derivative with respect to y of g inverse of y. Okay, so if you want to write that down, let me write it down more as like a formula that's convenient for us. What that means is that if g equals g of x, then the density of y with respect to y is just the density of x evaluated as what is u? U was g inverse of y times the g inverse of y dy. Is that making sense? So just to give you an example of like this is not like a formula like I would expect you to memorize, but just to give you an example of how you would use it in practice. So if you remember, like just to compare with it looks a little bit complicated, but like for example, like just based on the one we did last time with the exponential. So for example, if g of x is the exponential, think of this as y equals g of x, right? What is g inverse of y, right? Is well, you can say that if you take the inverse of like the exponential is logarithm, right? So you can just think of ln of y equals like, let's see, the inverse of y is just ln of y, right? And so the derivative of the g inverse of y with respect to y is the derivative of the natural log with respect to y, which is 1 over y. And so this is saying that that the that the density, so for example, this is saying that the density for e to the x at y is just the density of f of x evaluated at g inverse of y, so ln of y times 1 over y, and I believe this is oops, yeah, that's like essentially what we found before. It's just that I had used like slightly different notation, but um, in the previous example, I called that I called these functions f and g, but now I'm using g for a different purpose. But it is like the same, it is the same expression that we found before. Is that making sense? So that gives you like a formula. This gives you a way to relate the densities of a random variable and a function of the random variable, at least when they are related by a formula that by a function that's like satisfies this condition of being increasing. But again, there are many cases where that does happen. Like many cases of interest where the function is that. Um, okay, and that is enough to justify what's called the law of the unconscious statistician, which is something we have already used. Um, but it's kind of useful to see written down explicitly so that you know that it is actually like a theorem, something that needed to be proven. This is sometimes called the Lotus rule. It just says that if you have a random variable, which is g of x, in fact, this g of x doesn't need to be, the function g doesn't need to be like increasing or anything like that. So it works in more generality. But I'm going to prove it just for the special case that we have where like g is increasing so that we can use the previous formula. It just gives you like a formula for the Lotus, like the rule for Lotus gives you like a formula for the expected value. And so it just says that the expected value um, of y is just the integral from minus infinity to infinity of g of x times f of x. So for example, oops, sorry about that. So for example, if you just to continue with this exponential case, in the exponential case, if g of x is e to the x, what this is saying is that the expected value of e to the random variable x is just minus infinity to infinity of e to the x f of x dx. So you kind of, what this is saying is that you can kind of use the same distribution, like density function, with the difference that now instead of like putting just like the variable x here, you put like g of e to the x or g of x more generally. Or like another one is g of x is x cubed, then what this is saying is that the expected value of e of x cubed would be just x cubed f sub x dx, which again, we kind of implicitly use that already, but now I'm kind of going to justify that a little bit for you. It is so natural that you can easily not even think that there's anything that needs to be proven. That's why it's called the law of the unconscious statistician, because like it's so natural that like you don't even think you could ask, well, what needs to get proven here? You see, so that's why that gets this name. So it just says that when you compute expected values of things that depend on the random variable x, you can kind of compute it in the naive way, which is just like use the density of x and just like replace the instead of putting like just like x here, you just put like the expression of the random variable instead. Is that making sense? So let's do a proof. When g of x is increasing. Well, so when g of, in general, like the thing is like the expected value of a random variable is always like the integral of y or I mean of x, or in this case y, because that's how we're calling it, times its density. Okay, so this is actually the definition of the expected value in general. Okay, so it's like an integral with like this is kind of like an integral with respect to y. That's maybe that's more easier to think about it of why something needs to be proven, because the way I'm writing the integral, this is an integral with respect to y. I'm saying that you can kind of turn it into an integral with respect to x being the original random variable or the original variable. So it's kind of like a change of variable form. In fact, the proof will be more or less like the standard change of variable result from calculus. But I'm just saying that if you think about it in terms of like the names for the variables that you're using, it's more clear that they're like they don't look exactly the same because one depends on y and the other one depends on x. Is that making sense? So these would be the integral of y. What is f sub the density for y? The density for y is precisely this. So let me change that back. Copy here. Paste it here. Oops. Y. And now you do like a change of variables because y is kind of like it looks a little bit circular, but it is a change of variables for like a change of variables that I'm about to do because you can write y as g of x, right? So this is kind of like this thing about differentials, like that. What is dy dx? Well, that's g prime of x, right? So dy equals g prime of x dx. Okay, so this is going to be the integral from minus infinity to infinity of what is y? Well, y is g of x. What happens with the first red thing? It becomes f sub x of g inverse of y, but y is g of x. And then let me, okay, let's see. I should have, okay, this is going to be, let me work out this separately first. So this would be, let me put it like this. If this y is g of x, then that means that x is g inverse of y. Okay. So this becomes a derivative of g inverse of y. But that's a derivative of x. And then dy is g prime of x dx. Let's see. Okay. But what is g prime of x is dy dx. So maybe let's write it as, it looks a little bit silly, actually. It's so stupid, but it's kind of like works. This is dy dx. The thing to realize, again, which kind of looks a little bit weird, is that this is why like this Leibniz notation is actually a little bit better than the usual Newton notation for the derivative. In a sense, like this is kind of, I mean, you can actually prove that more rigorously. This is kind of like these two do cancel out almost as if they were like ratios. So they cancel out. So you just end up with an integral from minus infinity to infinity. You have g of x times f sub x of x dx, and that's what we wanted to prove. So I mean, again, it's kind of playing a lot with like the formulas, like the change of variable formulas, but so it can be a little bit confusing on what you're proving or not proving. But I'm just saying that there there is like a subtle point about like computing the expected value with respect to the new variable, which is y, versus like the old variable, which is x. But like what this Lotus law says or Lotus rule says is that more or less kind of if you had not realized that difference, like you would have been fine because you can compute the expected value in the naive way. So but it's like a fun application of like different concepts that involving the random variable. So that's why I thought um, that it was worth just discussing it a little bit. But again, this formula does work for g of x. That's not necessarily like an increasing function, and that's why we were using it also for like the second moment and things like that. So, but it's kind of good to know that there is like a law that guarantees that this works. Is that making sense? So now we can move slightly into something different territory, which is this stuff about up to now I have been talking only about a single random variable. So now we can talk about multiple random variables at the same time. This is sometimes called joint random variables. So this is a slightly new topic, but you'll see like the many ideas will look familiar. So like this just means like multiple random variables. In fact, they have been in secretly behind some of the things we had done before. So it's not that it is completely new, but again, one of the things about that happens in this probability course or like in probability theory is that sometimes you're computing things like the same thing just from different perspectives or under different names. So like many of the problems that will involve these joint random variables, you could kind of technically have solved them already with what we have seen. It's just now we're kind of like re, re, relabeling or naming this in a different way. Okay, is that making sense? So what's the classical? In fact, for now, I'll talk with just a lot of things can be understood better if you just talk about this with two random variables. So, and before doing that, this is why I had asked you if you had knew a little bit of linear algebra. So this is again, it's not that too much of what I would say relies on that, but there's a slightly it's nicer to interpret some of the formulas that I'm about to give you. Like if you have, if you know some a little bit of matrix notation. So I'll start with a discrete case. So we're going to start back to when the random variables have like a finite number of values or like finite number of outcomes. So let's recall in the discrete case. What was a discrete random variable? It was a random variable that has outcomes x1, x2, xn, right? Let's call this m. So a discrete random variable can only take m different values, and each of these outcomes has probabilities, right? P1, P2, PM. Okay, now if you remember the formula for the expected value, right, it's just like the sum from I equals 1 to m. Before I would call this n, but that's like less more of a cosmetic difference, right? So that of pi times xi. Okay, now here's a question. And in fact, that actually is something you would have seen since you took multivariable calculus. Where before have you seen a formula that multiplies some numbers and then adds them together. What sort of formula from multivariable calculus or even physics one you would see that has like that property? What formula involves like a sum of products?
Dot product?
Yeah, it is a dot product, right? So this is a dot product. So, and again, this hopefully everyone remembers like a dot product. So what you can do like is define like you can call it like an outcome vector. I don't know. Let's maybe to not confuse it with the name for the random variable. I'll like let's see. First, you can define what you could call like a probability vector. Okay, so let's call this P a probability vector. Which is it's literally just the entry, like the different probabilities like organized in some order. So let's call them P1 up to Pn. So a probability vector is just any vector whose entries are all non-negative, right? All the entries are non-negative and the sum of the entries add up to 1. So that's what a probability vector is. So the entries are non-negative and add to 1. And then what makes sense is to X, like the outcomes of the random variable, you can also just collect them into a vector. We can call this the outcome vector or X. Let's call it like, I mean, I guess it won't be too confusing, but like I'll put like a subscript for which says out for outcomes. So this would be, I mean, you could write it as sometimes it is called like a row vector. If you have seen that before, in this case, you could also write this other vector as a row vector, but you can also write it more conveniently as a column vector. So, I mean, it's the same vector. That doesn't make much of a difference. Is that if you do it this way, then the expected value, which was this sum, there are two ways to think about it. You can think about it as a dot product between the probability vector and the outcome vector. So it's P dot X as a dot product. And in fact, let's call this piece of X just to emphasize that this is like the probabilities for the related to the random variable X. Okay, just to emphasize that. But again, this is like the only reason why I asked you in the announcement whether you have seen matrix multiplication. It's just nice to know that there's like an elegant way to write the dot product. If you know matrices, you can write it as a dot product between the probability. If you can just write it as a matrix multiplication between the probability vector and the outcome vector. So you can literally just write this as without any notation, any extra notation. You can think of this as a product of matrices. Because again, if you haven't seen this, don't worry. This is like the first one is what's called like a row vector. So a row vector has size 1 times n because it has m columns. So this has size 1 times n. And the outcome vector is a column vector. So it has m rows and 1 column. So it's a matrix that you would call m times 1. And there's like if you have seen matrix multiplication, then there's like a rule that says that when these two numbers match, you can multiply the matrices and you get a matrix of the size of the outer numbers. But a 1 by 1 matrix is just a number, and that's why you end up, you can actually think of the dot product as a matrix multiplication. But in order to do that, one has to be written as a row and the other has to be written as a column. So except for that, it's kind of it is an I've seen before. Is that making sense? So again, if you haven't seen this early before, it does. Don't worry because I won't rely on this, but it's just like an elegant way to think about it. It just and just noticing that it's like a dot product is kind of like an interesting thing to notice, anyways. So you can think about that as you can think of the expected value as some sort of like dot product. Okay. So that was more like a notational aside. Now let me start telling you a little bit about the the case when you have multiple random variables. So now let's say you have two random variables, which I'll call x and y. So for example, x could be the result, like, x, you have two dice. And so like, here's where like this could arise. So here's some examples where you could like, you have two random variables. So you throw two dice, and then x represents what you get on the first die, and y represents what you got on the second die. Or more like of a physics example, you could have like particles moving along the x-axis. Along the x-axis. And so x could be either the position or the velocity, depending on what you care more about, or even the acceleration, right? Obviously, it could be different quantities. So x could be like, for example, the position or velocity, etc. The first particle. And y could be I mean, in this case, it's a slightly, I mean, that's slightly different case of the die, because the die has only finite outcomes. The position, like if you think of it as being continuous, it will be more of like the situation we will analyze a bit later, but it is a natural situation where you would have more than one random variable. So this, it qualifies under this thing about the, just looking at examples where you could have more than one random variable. If you otherwise, if you prefer, if you want to do like a discrete version of the position example, you could have like, again, like you have a couple of boxes and you have like the two balls, and so x represents like the position in which box like the first ball is located. Like you can think, to make it more concrete, like you could think of one ball as being red and the other blue. So x could be the position of the, in which tells you on which box like the red ball is, and y on which box the blue ball is. Or like, or box or on which box like a particle would be located. So I'm just trying to say that there are many situations where, you could just naturally have more than one random variable. Is that making sense? So, um, but in our situation, like we care about, we're still just to develop some intuition, where in the case where like they only take a finite number of outcomes. So let's just say that let's say that x takes outcomes x1 up to xm. So m outcomes, and y takes n different outcomes. So takes outcomes, or takes values y1, y2 up to yn. So if you notice here, I'm allowing for the possibility that m and n are different numbers. So in the case, like, in the case of throwing two dice, each has like each six faces. But then you could have like a different version of this would be like, an experiment where you throw a die and a coin. So you have like a random variable that only has 2 outcomes and a random variable with 6 outcomes. Or like even in the position like that, for some reason, like, you know, one ball is allowed to be on possibly more boxes than the other. So, you know, it's very easy to modify the situation so that different number of outcomes are allowed for each random variable. So it's better to just have it like in the case where, you know, that these two numbers do not agree, how many outcomes there are. And so what you can do first is define like the joint probability function, what's called the joint probability function. Which I'll denote as P sub ij, and that would just be the probability that x takes the value x sub I and y takes the value y sub j. So like, again, like we have done this a little bit before, like, and that's why I'm saying that in a sense, we kind of have done this already. It's just under different terminology. So if the experiment had been like, you know, throwing 2 coins just to make it easier, because otherwise I have to, so X could be 1 or 0, right? And, or let's call it 0 or 1, maybe I think that's better. So 0 or 1, right? And Y could be 0 or 1. So, you know, you could have like this is like the first outcome, or well, let me write it in the opposite order because like at least the notations will, it won't make too much of a difference now, but so this is like so x1 is here 1 and x2 is 0, and the values for the coins could be 1 or 0. So y1 is 1 and y2 is 0. Right, so something like P1 1 2 for in this notation just means or P sub 1 2 just means the probability that x equals 1 and y equals 2. Right, so this is the probability of, well, x being 1 for coins, usually that meant for us that x equals heads, right? That you got a heads, and y equals tails, because I think the convention we have been using is heads for 1. So, and I mean, again, this probability is something we had computed before. It's just under slightly different notation. In this particular case, if you assume with the usual restriction, like, you know, implicit assumption that the coins are fair, etc., this would just be 1/4, right? Is that making sense? But so how many of these numbers, how many numbers P, I, J are there? Well, you know, you have M options for the first random variable and N options for the second one. So there are M times N different probabilities, right? Or so there are M times N numbers. Is that making sense? So what's going, again, like this is more like a notational thing. So it's just like an elegant way to say it is that these numbers, again, in the case of coins, it would be 2 times 2, 4. And we already knew that there were 4 outcomes when you throw 2 coins, right? So that's kind of reasonable. Or in the case of die, it was 6 times 6, which is 36. If you're throwing like a coin with a die, that would be 12, right? 2 times 6. So I'm just saying, like, again, it's kind of stuff that we already knew, but now we're just looking at it from a slightly different perspective. But what you can do then is to assemble these numbers, if you have seen this before, into what's called like a matrix. So you can assemble, define a like a probability matrix or a joint probability matrix, which is just like a matrix whose entries are these numbers.
Professor, I had a quick question.
Mhm.
How come you said that P of like X is equal to 1 and then Y is 2? It wasn't exactly.
Um, like you mean, oh, I get you. Like, you mean that it should be 0?
Yeah, okay, I got you.
Yeah,
That makes more sense.
No, thanks. Yeah, it's just I put 2 this is like what I was. That's why I was hating myself for like the fact that the coins are 1 and 0, because then
Mhm.
like the notation looks a little bit ugly, big, because the second value is 0, so like it's just confusing. But it's just better it's kind of like it's unusual to say that in matrices, because I know you took linear algebra, right? Like in matrices it's kind of weird to say, oh, this is a 0th row. You usually say this is the first row, the second row, the third row. Like, so when you start counting rows on a matrix, you start from number 1. You don't count from number 0. So it kind of just messes up a little bit, like your like the numbers in your head. But no, but yeah, thanks for pointing that out. So they're n by n, not m times n numbers, so you can assemble them into a matrix. So create a matrix, which is I mean you can call it capital P, or let's call it P joint. So this is called the joint probability matrix, or I'll call it like that. And this is just a matrix whose entries are, P11, P12, P13, blah, 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 up to P1n. So it has m row, I should say, it has m rows and n columns. Then P1, P21, oh my God. So then it would be like P21, P22, P23, blah, 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 P2n. And it continues depending on how large is your matrix into PM1, PM2, up to PMN. Is that okay? So again, it's not indispensable, but it's kind of nice to organize the information in that way. And so this is like a matrix. What are the, well, at least at a minimum, each entry is non-negative, right? But there's a little bit more that we can say. Okay. In fact, what should have, okay, so what are some properties of this matrix, right? Some properties of these numbers. Well, each entry is going to be non-negative, right? Because we know probabilities are, and even more than that, they're probabilities. So each entry is between 0 and 1, right? But what's more important is like we know a little bit more. We not only know that each entry in the matrix will be between 0 and 1, we also, so for example, for 2 coins, right, which are there, like maybe I should put what this matrix is, right? It's a quarter, a quarter, a quarter, a quarter, right? And then if you had, if one, we can also do it for 2 coins just to make it more exciting. Like, when one is biased, so let's say that, where heads is 2/3 for one coin, and heads is fair for the other one. Let's say for the first coin, heads appears with probability 2/3, and the second coin is fair, so it's like um heads appear with probability 1/2. So in this case, the joint matrix, right? What would be? This is 1/1. Sorry, again, this is like this weird notation. 1/1 is heads, right? So what's the chances of getting heads? Well, you have to assuming that the coins are independent, right? You multiply this probability, so you get 1/3. Then this would be heads in the first one and tails in the second one. Right. So this is still 1/3 because the probability for tails is 1/2 in the other one. Then this is tails in the first one and heads. So this the 1/3 times 1/2 is 1/6. And the other one is 1/6, I think. Right. So like just to help you a little bit, this would be heads, tails, heads, and tails. Oops, sorry. Is that making sense? So, like, for example, what's a property that you see? Um, what's the fact that is happening here? When, let's say, you take this joint matrix, right? Joint probability matrix, you add up all the numbers here, all the entries, or you add up all the entries here. What number are you getting? What's the sum? Yeah, you just get one. Good. And that's kind of like makes sense because let me write it like this. That makes sense. It's kind of like a law of total probability saying that something must happen, right? So this one means like something happened with certainty, right? Because this is kind of represent each of these P I sub j is representing a particular situation, right? Where you got like some outcome, some specific outcome. So since we have like only n times n possible outcomes, this is saying that with certainty we will get an outcome, right? So this is just saying that something will happen with certainty. So it is just like the generalization to the case of two variables of like this constraint that we had before that the sum of the probabilities had to add up to one. Is that making sense? So it's like the generalization of that to multiple variables. Okay. But then in fact you can work out this formula in two different cases, from the two different perspectives. So let's see. Let's just think. Let's go back to. Okay, let's just start here. So we had that this had to be equal to 1. But let's just write explicitly what p sub ij is. So this is just saying that x had to be take the value x sub I, and y had to be take the value x y sub m, y sub j equals 1. But I mean, again, it's just kind of rewriting what we had done before. Like this, you can think of this comma as some sort of intersection, because this is saying that x is x sub I and y equals y sub j, right? So does that making sense? But then the probability of an intersection, one way to write it down, if you remember like the definition of like the condition of probability, it is like this. Right, like and if usually like we use like the conditional probability formula the other way, but like one way to use the formula for conditional probability is that, the probability of an intersection is like the conditional probability times the probability of one of the events. So let me put it like this. Okay. Because again, what is this by definition? It's just the probability of the intersection divided by the probability that y equals y sub j. But now let's just focus over, like, let's just think about this for a moment. If you look at this sum, right, you're adding up, like in this sum, if you just look at the sum of the interior, right, like I is fixed, right? So I is fixed. The only thing that's changing in this first sum is the sum over j, right? So this is like kind of, I mean, we had a name for this, right? Like what do you think this should be equal to? Is that making sense? I don't know if you remember this formula that you can break like a probability as a sum of conditional probabilities times the probability of that event, because you know this is just saying like, to know what's the probability that you find the value of x equals x of I. Well, it just since y has to take some value, those are disjoint events. Like the different values of y are disjoint events. So you can just condition on that on each potential value for y times the probability of that value of y occurring, and all of that should add up to the probability for x equals being x equals xi. Is that, I don't know if is that what we had called before the law of, I don't know if that was the name that we had given to the law of total probability, but it was definitely one of the formulas we had seen before, right? And so why is that useful? That's just useful because it is saying, right? But again, what is it that this thing that we started with? That was the sum over the j's of the piece of ij's. So this thing, so let me write it this way. The probability that x equals x of I is then the sum over the j from j equals 1 to j of a piece of ij. So that's just saying that if you add up, what does it mean? What does that mean? That's just adding up the elements in the varying the elements in the of the column for a fixed row. So this is a fixed row. As you vary j, you're varying the column. So in other words, this is saying, like, just to go back to the matrix notation, because this is useful here. So what I'm trying to say is that if you, let me use a specific color. What I'm trying to say is that if you add up all the elements in the first row, you get the probability that x equals x1. If you add all the elements in the second row, you get the probability that x equals x2. And so on until the last one, where if you add up all the elements in the last row, you get the no, I'm good, running out of colors. I don't know. Okay, you get the probability. I don't know what happened. This there was a new version of Notability app, which is kind of annoying, so we're stuck with it, I guess. What happens if I delete it? I don't know. Let me delete this one, which I don't care about. Huh. Oh, this is good. Is that making sense? Is a more is the formula making sense? So I'm just saying that by adding up the rows, you can get the probabilities that each that the random variable x takes the different values. In a sense, this is called this is what is called usually the marginal probability, because it appears at the margins of the matrix or of the table. So if you wrote it as a table, like as an Excel column, it is kind of at the end of the column or the margins. So this is, so you can define, or you have that the probability. So this is like kind of like this is sometimes called like the marginal probability for X. Because again, like in this picture, it's just appearing like at the margins. So it's kind of, and then there's nothing special about the X. If you do the same for the Y, then you would get, if you add up, if you fix a column and then you add up by varying the rows, then you get the probabilities for the Y sub I's. So I can put it here more visually. So what it would be, this would be, for example, this is the probability that Y equals Y sub 1. And then this one, the next one would be the probability that Y equals Y sub 2. And the last one would be the probability that Y equals Y sub n. Is that making sense? But again, you see, we're not doing kind of anything new. We're just giving like some new names to things we already had computed before, in a sense. So it is, I think, very intuitive that this is how this is supposed to happen. but it's kind of nice to just like, see it in this notation. It does add a little bit of different perspective to what's going on. Is that making sense? And then in the in the what happened when you had we kind of did this with when we had like two events, right? And when we had two events, like what makes sense to us specifically was whether the events were independent or not, right? So the most straightforward analog of that for random variables, um, let me give you the definition. If what's going to happen? That the probability that x equals x of I and y equals y of j, right? What should that be? It should just be the product of these two probabilities. Is that making sense? Like again, it's hopefully you will believe me that this is the most um, natural generalization. It's just like the independence of events, but now for each possible value of the random variable. Is that okay? Is that making sense? And in fact, there's an elegant way to write. Like again, this is where the matrix notation kind of makes things a little bit more elegant to write it down. Uh, because this is kind of like a statement for each entry. This is a statement for each entry of the matrix, right? Um, it's saying that each entry of the matrix is kind of a product of two probabilities, right? Oops. But there's like a more like global or holistic way to think about it, which is like in terms of the matrix notation. So I mean, like I don't want to spend too much time on this because not everyone may have seen the matrix multiplication stuff. But if you think about it as a matrix, or as another way to say this using matrix notation, the matrix itself, let's see if I get this right. It would be uh, the probability vector of x times the transpose of the probability vector of y. So where this would be like the probability vectors for x and y. So if, again, just to explain this to those who have seen this matrix notation, the reason why this works is that if you remember the probability vector at the beginning, I wrote it as a row vector. So, oops, where did I write this before? It was a row vector. So it was a vector of size 1 times m. Or, oh, okay, I'm writing it as row vector. So this is Let me see. Maybe I'm getting the numbers like I'm writing already like the transpose should be in the other one because I already decided to write this as a row vector. So like yeah, let's see. So this is right. The probability vector was a row vector. So for example for y this would be a vector of size 1 times n because it's a row vector. And then this is what's called the transpose of a matrix. So it just changes the row into a column. And then this originally without the transpose, this would have been 1 times n, but when you transpose it, it becomes n times 1. So yeah, again, the matrix multiplication makes sense. These go away and then you just end up with the n times n matrix. Okay. So in the independent case, the matrix can be obtained just like as a product of the individual probability vectors, which is like again like just like an elegant way to think about this definition. But again, you can just stick with this definition. And in practice, that's kind of like maybe how you would check it anyways. That works. Is that making sense? Um, the cool thing of writing it this way, again, for those who took linear algebra, there's like a concept of the rank of a matrix, which you may have seen. That just means that when you reduce the matrix using Gauss-Jordan or to get to row echelon form, the rank is just the number of of non the rank is just the number of non-zero rows. If you can write the matrix, any matrix that can be written in this way, you can show that has rank 1. So this matrix is have rank 1 actually in the independent case. So just as this is more like a theoretical curiosity. So as a remark, this means this in this case in the independent case the matrix will have rank 1. So it's kind of something that you wouldn't maybe think about any like because this seems completely like uh as an aside from the probability question, but it's kind of like a curious property of like in terms of the linear algebra perspective. Uh, is that okay? So again, kind of today what I'm doing is just giving you a bunch of like concepts you already knew, but in this new notation. But in practice, it is similar to the stuff we have been doing before. It's just like all is now decorated with this new notation. And then kind of like following this law, Lotus law, like this law of the unconscious expectation. Um, if you had a function of two variables, what are two functions of two variables that we could be interested in? F of x, y could be like x plus y, or f of x, y could be x times y. Those would be like the most interesting functions of two variables in probability, or two of the most interesting functions. then the expected value for f of x comma y is just going to be the sum over ij of pij f of x I y j. So just to give you an example of what that means for each of these two functions I just wrote. So what would be the expected value of x plus y? Well, let's start with x times y actually, because there's nothing else that I can work out here. But what's the expected value of x times y? Expected value of x times y is just, according to this formula, it would be the sum over I and j from 1 to n of pij times xi yj. Which again is maybe what you would have written down anyways if you haven't thought about it too much. But I'm just saying that it is like as a fact, it is what you would have expected. Um, so you just like, kind of multiply, do all the possible products between the values of x and the values of y, and then you average them out using the probabilities for the occurrences of those values. Okay. So it again, it's kind of like a reasonable formula to have. And then what would be the expected value for x plus y? That would be the sum from I equals 1 to j. Sorry, this doesn't require the indices could be different because I goes from 1 to m and n and j goes from 1 to n. Sorry about that. So what would be the sum? What would be the expected value for the sum? Well, what you would expect is that you add up the possible values of the x's with the y's. You would do something like that, and then you just multiply it by the corresponding probabilities because it's sort of like some sort of like average. Is that making sense? And now, if you remember, like the expected value, what would you like this to be? What would be a nice property for this to have if things work out nicely? Should be the expected value of x plus y?
Perhaps E of X plus E of Y.
Yeah, you would like that to be linear. So let's see. Yeah, you would like that to be linear, correct? So this is where, let's see. I mean, it's kind of like follows quickly from, let me just put ij of, you can distribute this, break it into two parts, okay? And then, yeah, like here, like you can use the fact that, like when you just have to be careful how you do this, but you can put it like this. So you're adding over y, you can sum first over j of the pij's times xi, okay? Plus, and then here it's more convenient to sum first over the i's. Why? Because now if you look at this, this is the sum where you have fixed the row but are varying the column, right? So you have fixed the row but are varying the column, so that puts you in the first situation. So that's literally the sum over I for the probability that x equals x of I times xi. And the other one is kind of the same, but with the sum in the opposite order. I mean, the index is first over I. So here you're varying the here you have fixed the, you're fixing the column and they're changing the row. So you are in this situation. And so that's a probability that y equals y sub j times y sub j, and that's by definition the expected value of x plus the expected value of y. Is that making sense? So the expected value is still linear over sum. And of course, there's, as you can imagine, there would be a generalization like to 3 or 4 or 5 random variables. And so like the same would happen. Like it's exactly the same proof. You just like kind of have to do the sum in the appropriate order to get the result. It's just that in that case, like, well, kind of like the matrix interpretation is more tricky because if you have 3 random variables, like there will be like an index I, an index j, and an index k. So it's kind of more like a 3D matrix. So it's a little bit different, but still, at least for 2 random variables, it looks very nicely to do in terms of matrices. So let's write that down in a box because it's an important formula. So the expected value of the sum of random variables is just the sum of the expected values. Is that making sense? And then, in fact, we can also talk about, let's talk about this one. How about this one? What in the ideal world, what could happen here? What would you want this to be in the ideal world? Yeah, that would be the ideal world. Uh, but that is like a little bit too much to ask in general. So in fact, what you can define is like the failure for that to happen, and that's called the covariance of x and y. So you can define the covariance. Just write it as this in this way, which is just the expected value of xy minus the expected value of x times the expected value of y. That actually is a fun exercise to check if you want. I mean, it's just playing around with the distributive properties and the linearity. If you want, like, I'll leave this as an exercise to try it. That this formula is the same as the expected value of x minus the mean of x. Remember the mean or the average, that's the name for it, times y minus the mean of y. So why is that? I mean, how will you check that? That you distribute break using the linearity of the expected value over sums, and that's how you would. There will be some cancellations, and that's how you get back to this. Okay. And just to make sure if this is making sense, what is the covariance? There's actually a covariance of X with itself. So what's the covariance of X with itself? What is that? That would be E of X squared minus E of X squared. What was the name for that?
Is that also just a variance?
It's just a variance. So the covariance is a generalization of the variance the standard deviation squared, right? So the covariance of X is just the variance of X or sigma X squared. So this covariance thing is kind of like the natural generalization of the variance to random variables. And then what's easy to check is that when X and Y are independent, then the covariance vanishes. So let's check that. Oh, in other words, the expected value of X times Y is just the expected value of X times the expected value of Y. And why is that true? Why is this true? Well, again, what is the expected value of X times Y? That's just the sum over Ij of Pij Yj. In the independent case, this Pij is actually it's just a product, right? So the Pij in the independent case is just Pi times Pj, just to just be a little bit sloppy with the notation. And it is I mean you can kind of do the sum first over the i's, like you can, or let's sum first over j. So it's kind of like a sum, since it's a sum over j first, like you can pull out the stuff with I because that's like a constant. So it's like pj yj, and that's like the expected value of y, but then that becomes like a constant, so you can pull it out of the sum, and this is pi xi, and this is just the expected value of x. And so, I mean, you can move it around if you prefer to see it in the opposite way. Uh, it is a fun exercise to try to prove this, like using the matrix notation. If you like for multiplication, it's kind of fun. It is again, usually like the idea of matrix multiplication is that all these proofs like that involves these sigmas, you don't need to write them anymore, because that's kind of like secretly what the matrix multiplication involves. So there's like again like a slightly more elegant version of this. Um, that involves matrix multiplication. Is that making sense? Um, so far so good. I'm sorry if today I'm just throwing at you a bunch of definitions. Like next time I'll do some more examples, but it's just kind of laying out like the necessary machinery so that like we can discuss some more concrete things next time. Uh, Maybe just to give you a heads up, like the ultimate goal of this course, like now we just have two big things left, which is the law of large numbers and the central limit theorem. And that's kind of like what in two of the key aspects of probability in terms of its usefulness. So it is important to kind of get there. We almost have all the tools to prove them, or at least to give you like an argument of why it's true. I don't know if I would go into like an actual proof of that, but but what they involve is independent random variables. So that's why we're doing this small detour over multiple random variables and independence. Um, because we kind of just need to have some formulas ready to go once we discuss those two big theorems. Um, And then we need something called the moment generating function of a random variable, which is a version of the Laplace transform. I don't know if some of you have seen like the Laplace transform. It is an important tool like in electrical engineering or for solving differential equations. Um, so there's like the Laplace transform that you can define for a random variable, and that's kind of useful also to in the proof of the central limit theorem. So we only need a couple more things. We also don't have that many classes left, um, so we're putting kind of like the building blocks together for that, like the the less more important part of the two most important results of like probability theory, probably. So just to finish today, because this is kind of fresh, let me give you like a generalization to the continuous case. Like almost everything generalizes immediately. So, and then next time I'll do some examples. So what's the generalization to the continuous case? So now you have X and Y, two random variables that take continuous values. So that could be like the energy of a part, could well it takes continuous values like many quantities in physics, energy, velocity, momentum, things like that. So this is kind of more appropriate for like physics problems. The discrete case is more appropriate for like combinatorial problems or like signal analysis, things like that. So now this is like two random variables taking continuous values. And so the first thing, what we did here, if you remember, the first thing that we did when we had two random variables was talk about this joint probability function. The analog for that in the continuous case is like the joint density function. So you can call it like this. Well, it is what's going to be that? It's like a function that's you can make it continuous. Usually, in most cases, that will be continuous, anyways. But it's like a function that's non-negative and that has a property that is probability when you integrate it, it adds up to one. I mean, the analog of the sum, right? The important property of like this numbers piece of ij, right? What was the important property of this numbers piece of ij? That when you add them all together, you get one. The analog of addition in the continuous case is integration. So what this is saying is that when you do the double integral, because now there are two variables, so the analog of like the probabilities adding up to one is that the double integral from minus infinity to infinity of this joint density function That's just one. Okay. So that it's kind of like saying something needs to happen. And then I don't know how much you remember of Calc 3, but you know, there's this Fubini's theorem. How did you evaluate a double integral in Calc 3? Right? It's like you do Fubini, or like basically you do these iterated integrals. So for example, well, that's kind of implicit how I'm writing this here. So we'll do some double integrals or triple integrals next time. I'll try to. So you can integrate first, for example, over y if you wanted to. So this would be like an integral from minus infinity to infinity. The only difference is in Calc 3 there were no improper integrals, right? But everything else, we're in the world where everything is nice, so there's not much difference in that case. So you can integrate first with respect to y, and then integrate what you get with respect to x. But if you think about that, what should that be? Well, after, if you remember Calc 3, after you integrate with respect to y, once you integrate with respect to y, there can be no more y dependency, right? That's the whole point of doing the integral with respect to y. So the value for this iterated integral can only be a function of x, right? And that's actually would be like the density function for x. That's in analogy with the previous cases, what you would call the marginal density function. So this only depends on x. So this would be f sub x. This would be the density function for x. Okay. So like you kind of define, it is like the analog of what we were doing that before, that when you added up the rows, you will get the probabilities for x, and when you added up the columns, you will get the probabilities for y. Is that again, like now they're kind of like infinitely many rows and columns because of there are infinitely many outcomes each random variable can take. So it's kind of like doing like a continuous version of like a sum, which is like the integral. So this, so basically what I'm trying to say is that f of x is the integral from minus infinity to infinity of the joint density function with respect to y. And the same happens if you did the integral in the opposite order. It's kind of like the version of adding up the columns along the columns. Is that making sense? So those are the density functions for x and y. And then once you do that, what did we do next here? Well, we talked about the independence, right? So I can tell you, yeah, I can, oh, I told you first a law of total probability and then this independence thing. Well, let me put it this way. So first, like then you have like a similar concept for independence. So the independence of random variables in the continuous case, it's just that these density functions are split as a product. And then there's like, again, this Lotus law. So everything is the same. That's what I'm trying to emphasize. Everything is literally the same, just with integrals instead of like sums. So that's why I'm not redoing every calculation. Then you have the Lotus sum, that if you have like a function of x and y, then the expected value of that random variable is just the double integral from minus infinity to infinity, of f sub, let me put it like, sorry, I should put G because otherwise the notation would get confused. Gxy of the joint density function. So just to make it more concrete, this means, for example, that the expected value of x plus y would be the improper integral from minus infinity to infinity of x plus y times the joint density function. And the expected value of x times y is kind of the same. So again, you should like the important thing to realize here is that we're not doing anything new except for like putting integration signs instead of sum signs. Okay. And it still happens to be the case that you know, the expected value of a sum is the sum of the expected values. It's essentially the same formula. You just split it for like integrals. And it still happens to be the case that you could define the covariance if you wanted of, you know, the covariance of the random variable to be this thing, which will vanish when x and y are independent. So what I'm trying to say is that everything that I wrote before is still works, just for the, you know, for in the continuous case, you just put integrations. Of course, you have to be more careful in practice because with integrals there are more issues at play, like things could diverge or things like that. So I'm making like an implicit assumption that everything is like all the integrals are finite whenever I'm writing the formula. Okay, but I guess I just wanted today just to give you like a bunch of formulas to so that you would have them so that we have them ready to go for Friday. I think that for Friday what I'll do is just instead of having the quiz, I'll give you like an assignment for you to upload over the weekend. That may be better so that you can take some break from the exam, and also because I still haven't told you which problems to look for the the quiz. So yeah, on Friday we won't do a quiz. I'll just give you like a list of problems later on. But if now you see why multivariable calculus was a requisite, because if you want to compute expected values for two random variables, you will have to do like a double integral. And we will do also like a triple integral in spherical coordinates at some point to you find like this Boltzmann distribution for like the speed of a particle, not the velocity, which is slightly different thing. So you have to switch to spherical for doing that. But okay, I think it's like a place to end. So again, I'll try to finish. I'll start grading the exam between today and have them ready by tomorrow. So yeah, I don't, if there are any questions, I'm happy to answer. If not, I'll see you on Friday.
Have a nice day, Professor.
You too, you too. Bye.
Thank you, Professor.
Bye, bye, no worries. See you.